Right, welcome back Physics 30. Today's lesson is a continuation of nuclear physics. Lesson number 2, we're going to talk about this new concept known as decay. Now, when you think about the term decay, you may think about, for example, fruits. So imagine you put a banana or onion, apple outside, but room temperature room, something like that. And imagine you're putting it for more than a day or two in a summer day. Then what's going to happen? It's going to rotten. And let's think about rotten fruits. Fruit will rotten, and for example, if you have that much of size, it's going to get withered. And then it's going to turning into a smaller size fruit. So decay, when you think about the word decay, if you have this much of size, you're going to notice with certain time pass, it's going to be remain about this much because it's going to turning into something else. That's the decay. Decay reaction, if you talk about it in nuclear physics, there are two things that change, but mostly imagine neutrons are the ones that go away. There are some that have protons that go away, like alpha decay. So we're going to look at those. Before we getting into an actual calculation or any type of concept in this nuclear physics, I like to go through some particles. There are three different types of radiation that is being emitted when nuclei are unstable. And that will be involved with radioactive decay because they emit radiation as time goes. Really famous story that I can give it to you is, one of the first female who got the Science Nobel Prize was Marie Curie. She got basically a radioactive disease which turning into a cancer. And if you want to know Curie, she's the one who discovered was it radium, if I recall. In any case, when nuclei are unstable, they are radioactive and they emit radiation, and because of that the size becomes smaller. It was discovered that there are three different types of radiation, and when it comes to decay type, we're going to learn 4 types actually because of this beta particle. But in any case, alpha particle. Even in Unit B and Unit C, we learned about alpha particle in many different situations. Alpha particle is, first of all, if we use alpha, Greek letter, and positive to a charge. This is kind of like a helium actually, because if you think about 2 proton, 1 proton is hydrogen, 2 proton is helium. So basically alpha particle is, specifically now we can use nuclear notion, helium 4 nuclei. So I'm gonna actually open Physics 30 data booklet because it is important to go through some of the data using periodic table. If you look at 2 proton, and if I use it, helium have 2 proton, and 4 is basically the mass number for this specific isotope. The reason is because in that case we know that we have 2 protons and 2 neutrons. That's why. So in any case, helium 4 nuclei is alpha particle, and when it comes to the size compared to any others, it's the biggest, and thus it doesn't have a lot of penetratable ability. In fact, it can be blocked by skin, sheet of paper, 1 sheet, or few centimeters of air is good enough to block this particle. When it comes to our health concern situation, it is, however, dangerous to inhale or swallow, And because the reason is, can you see it's positively charged over here? It's gonna ionize some of your cells, so lung cells, those kind of situation, or digestive tract cell. That's one of the type. And we already know alpha particle from Unit B. We never talk about the second type, beta particle. Now, in Physics 30, we have beta positive and beta negative. In Science 30, we'll learn about beta negative whenever people talk about beta decay. So, let's talk about beta particle. Beta particle is basically very energetic electron. So sometime when it comes to this beta, you may see that some people use En -1 as exponent. So highly energetic electrons, and as you may know, electron size is smaller than alpha particle size, so you may notice it's more penetratable. Think about like you're throwing very sharp sphere versus wooden stick. Which one will penetrate? The sharp one, because of the smaller size of the surface area, right? So think about that. Beta particle can penetrate the skin. This is one of the main reasons why UVB radiation will cause skin cancer. Can cause skin cancer because it can destroy the DNA sequences in your body. It can be blocked by many sheets of paper. It can block by wood and few millimeter of metal such as aluminum. So it's still not as strong. And several meters of air. Penetration ability is really important to know for diploma questions actually. It is, however, dangerous for skin cell, like I mentioned. Whenever you have any cell that is contacting with the outside, it is dangerous because DNA sequence, the hydrogen bond inside, and the actual sequence, it can be destroyed, can cause mutation, that's why. And it's also dangerous when you inhale or swallow directly because it can ionize. But it's not as much ionizable than alpha particle because of its small size. It will decay relatively quick. Now, third, gamma radiation. The one that, Hulk, the green light that you see from the Hulk movie, Incredible Hulk, or the very first Hulk in 2004. Gamma radiation is emitted in space a lot. Fortunately, our atmosphere on Earth basically blocks these radiations. So that's a good thing. But in any case, very, very, very high frequency. In fact, that's the highest frequency. If you have very high frequency, that means it's high energy because the formula is HF. That's why. And H is basically the constant, Planck constant. An energy photon and have a greatest penetration ability. There is one metal that actually blocks them, which is lead. This is one of the reasons why all the roof during World War era was actually painted using lead, which is another reason why, if you know the movie, I'm going off track a lot, but Wizard of Oz, there's a Tin Man character, and the actor who played that role died due to lead poisoning because of the lead paint. So in any case, it can pass right through your body, can be blocked by several centimeters of lead, and a couple of meters of concrete, and several kilometers of air. So this is one of the reasons why air atmosphere, stratosphere, those kind of thing, if you learn about those in Science 10, those are the reason why gamma radiation doesn't penetrate to our land level. But know the fact that these radiation can penetrate directly through, can ionize any cell, even the bones, and it can destroy your molecular arrangement of your body, which can cause many different problems. But there are some tendency that gamma radiation, because it's so fast, that it ionizes not as much as alpha particle because of the duration of time that is interacting with the cell. But in any case, it's important to understand the penetration ability. So let's look at some of those theoretical examples. You have radiation source in here. Think about radium, any type. And then if there's a box that contain, and of course, this is not paper box, but I'm just saying as a box. It can be lead box or something with one opening. And you will observe any type. And the way that you determine what type of radiation is, just apply external magnetic field. External magnetic field. So one thing that I know is there will be a radiation that go directly, which will be gamma radiation, because gamma radiation doesn't have any of those bending ability, because it's EMR, light. Now, however, if it's beta particle, negative, then I should use my left hand rule. 4 fingers are going directly into the page and my thumb is going that way, my palm is going down. So basically you know that there will be circular motion that go like this, and that's my beta negative particle. If there is a beta positive particle, positron is what we're going to learn, then it's going to turn this way. In addition, we're going to have alpha particle, which will use right hand rule, and if you do that, it's going to turn upward, and that's alpha particle. You may notice that I draw different size of the circle on purpose because of the different mass and radius, which we're going to calculate in future. Now, what if you put it in electric field? Easy one first. Gamma particle, or radiation if you will go straight because that's an EMR. That's just part of the light. But if I think about beta particle will go towards a positive plate because negative and positive, they attract each other, right? Another part, what about alpha particle? Alpha particle will go towards negative charge. The reason that I put a little bit of a faster drop to the plate or fall onto the plate for alpha particle is because, well, the charge is 2 to 1, right? So you're going to have more attraction for alpha particle. This is how we scientists check. If something is radioactive, we need an external magnetic field or external electric field. Doesn't matter which one you choose. And in real life, we generally experience low amount of background radiation. And generally, the main source that go is sun, because sun undergo nuclear fusion. But the thing is, we're receiving it as a low intensity. So that's why it's not going to harm the cells as much. But if you think about radioactive treatment for cancer patient or something like that, it does not only kill the cancer cell but also can kill our immune cell too, which makes the patient more vulnerable. But in any case, if you are exposed for a long time, like short-term dose of huge radiation, those kind of situation, it can cause radioactive sickness. And those are very prevalent when it comes to any type of, how can I say, places that experience either meltdown of nuclear power plant or any type of seepage from nuclear power plant. Those are very important to consider, like few years in Japan, something like that. All right. So let's talk about actual decay reaction. Now, first thing that we need to understand is how we balance nuclear equation. And when it comes to balanced nuclear equation is, well, we need to think about two things. And I'm going back and forth from a data booklet, so please understand. Conservation of charge, net charge, and conservation of nucleon. And this is available on your data booklet. I believe conservation of charge is number 7 of your physics principle on data booklet. And when it comes to the second one, that's number 8, conservation of nucleon. Now, one thing that you need to understand is, first of all, the term nucleon. What is a nucleon? Nucleon is basically the number of neutron plus number of protons. So it's basically a mass number. And number of the charge is basically, if it's unit B, that's like negative charge. Like think about the conduction of identical sphere. But when it comes to nuclear physics, it's a bottom number. It's a proton number. So that's why I said over here, top number, use conservation of nucleon, which is a bottom number. Oh, sorry, top number. And if it's bottom number, it's a conservation of charge, which is the bottom number. So top number, talk about mass number. Bottom number, represent charge number. So let's do some example. Alpha decay. So that's fancy way of saying you emit helium, something like that. So let's talk about our alpha decay of radon 222. It's a good idea to go to your periodic table in your data booklet. So where's that page? Page 1. Radon is basically located on radon. Oh, sorry, that's a radium. Radion is RD. Yeah, RN. Radon is RN. 86 at the bottom and 222 on the top. Now, if you think about it, in chemistry too, there's a left side and right side. In the world of physics and any type of decay reaction, you should have left side and right side. Except what we name for left side is parent molecule or parent nucleus. And when it comes to right side, you have a daughter nucleus, which I'm gonna talk about it. Think about reactants and product. So first thing first, alpha decay. Alpha particle need to go like this, and then 2 to 4, or you can put it as a helium. 2 and 4. Doesn't matter which one you use. I may use this format more. And then when it comes to my final product, which we call it as a daughter nucleus, here's what you need to do. It's a simple subtraction and addition. 222 minus 4. Basically, what that is that will give you 218. And I'm just gonna 218 on the top. There you go. And at the bottom, 86 minus 2, which is 84. And those tells you your charge number and mass number. Mass number may not tell you a lot of things. However, charge number, you need to find it using your periodic table. What is 84? That's polonium, so it's PO. So my left side is now included just one radon 222, and that is basically how can I say, the isotope notation of parent's nucleus. And when it comes to product, you have alpha particle followed by this one, which I'm going to say is daughter nucleus. So that's basically how we write down alpha decay particle in here. If you want to think about it as a conservation of momentum situation, here's what it is. Initial momentum is equal to final momentum. Initial momentum is basically momentum of radon 222 originally, which should be equivalent to P alpha plus P polonium 218. Energy conservation perspective, same thing. EI, EF. So basically, my energy that I have is $218, and basically that's what it is. You can find my delta E using mc square because mass can be a little difference between these two. But we are not doing the calculation at this specific question. We are gonna do that below. So let's do some calculation example now. Gonna prepare some calculator if you don't mind. That's oh, there you go. What is this page? There you go. So let's see. When a parent nucleus at rest undergo alpha decay, the daughter nucleus is francium-223. The alpha particles emitted. First of all, we need to find out what's on the left side. Parent. But we have daughter given 223 francium, which is Fr. If you use your periodic table, where is that located? It's located at 87. So that's francium. And when it comes to alpha particle, that's helium. That's 2 and 4. So that means if I add them up, 87 plus 2 is 89. That's a conservation of charge that I use. And then 223 plus 4 is 227. Make sure that nothing is lost during this process. Conservation of number, basically. So 89 is basically, oh, where's my 89? Acynium. There you go. AC. So, identify parent nucleus. Now we can answer. Our parent is basically AC227. There you go. So now, B, determine the recoil velocity. Now let's think about it. First thing first, we can assume a conservation of momentum. So basically what you can do is Pi is equal to Pf, and we can basically put Pi is 0 because the question says the parent nucleus was at rest. So that means it's 0. That means my final momentum, which is P alpha, P FR, there are 2 momentum. So we can use that as right side. My momentum for alpha particle can be like this. Now, that is M alpha V alpha plus, where is it? Plus M francium V francium. You can put it in that way. Now, one thing that we know is we know alpha particle speed, mass, and we know the mass of francium, but we don't know the V. So let's rearrange the whole thing. We can say M FR V FR is equal to M alpha V alpha, and VFR, that is equal to M alpha V alpha over M FR. There we go. And that's what we can do. And we can punch these number in now. Mass alpha particle 6.65, 10 to the power negative 27 kilogram. Velocity is 5.80, 10 to the power of 6, divided by mass. You gotta be careful. You need to use real mass. It says 223.0197 U, which means you need to multiply with your conversion. 1 U was equivalent of proton mass almost. There's a table that you can find. And now we can punch the number in. It turned out 1.04. Of course, you need to round it up in this case. 1, 2, 3, 4, 5, 10 to the power 5 meter per second is a speed, recoil speed of the daughter nucleus. So I use conservation of momentum as, how can I say, as a little bit of an assumption. Now, determine the mass defect. This is quite tricky because we need to go through energy perspective. Mass defect and energy from it, which I'm gonna put E and delta M. Basically, this is how mass converting into energy, and we have our energy of final is given. The reason that I know is because we have kinetic energy of alpha particle, kinetic energy of daughter nucleus, which is francium. So I can actually do 1 over 2 mv square and 1 over 2 alpha v alpha square and francium v francium square, something like that. So we can punch these number in to find out the total energy in final. For 2, velocity. And that's a 1. I gotta find out the mass again. I didn't save it. There you go. And let's punch the number in. This may take some time. There you go. 1.13. So we got 1.14, 10 to the power of negative 13 joule. And that is basically coming from our mass defect energy, delta mc squared. So delta m is equal to 10 divided by square kilogram. And delta m, I can just punch those number in. 1.27, 10 to the power of negative 30 kilogram is mass defect. That's what you can do in decay reaction and calculation. I believe that's a good amount of lesson that you can do for today. So I'm gonna give you what you can do. Basically anything related to alpha decay. So question number 1, 2A, D, or more likely an actual question, 3, and 5. One particle, 6, and I believe that is good enough. That is today's lesson.